Welcome back to our heat transfer class, where we are delving into the use of numerical methods for solving heat conduction problems within solids. This video was made with the support of Energy. After the introduction to the application of numerical methods to heat transfer problems, let us focus on the energy balance method. This lesson is divided into several parts. Let us recall the concept of discontinuous physical model. The application and solution of the heat diffusion equation implies assuming a continuous model of matter. However, there is a way to find the temperature distribution inside a solid without solving the diffusion equation. The energy balance method is based on dividing the medium into a sufficient number of volume elements, domains, or nodal regions, and then applying the energy conservation equation to each element. This division is known as meshing. In this way, a system of equations is obtained, one for each element. As will become evident, this approach enables to analyze many different phenomena, such as problems involving multiple materials, embedded heat sources, or exposed surfaces that do not align with an axis of the coordinate system. This method is based in the hypothesis that in each element, called domain, temperature is uniform, the properties are uniform, and the heat generation, if it exists, is uniform. The node is the representative point of the domain, in principle, the center of mass. Anyway, the node position within the domain is something we can discuss later. The first consequence is that we no longer obtain a continuous function of temperature, but values of the temperature at discrete points. What we have is a vector of temperatures. The more nodes we have, the larger the vector will be. Due to the hypotheses, the finer the mesh, the more the discontinuous description fits the actual physical system. In addition, the finer the mesh, the closer the discontinuous solution is to the continuous solution. The error is thus proportional to the increment of x, y, or z. However, the more elements we have, the slower the calculation and the more memory we need. In solving engineering problems, we have to reach a compromise solution between precision and the necessary computational resources. In many cases, results obtained from a coarse grid are satisfactory. Selection of the appropriate grid is a judgment that must be made by the engineer. Energy balance at each node. Once the domains and the position of the nodes have been defined, our discrete model of matter, we can make the energy balance in each node or domain. We apply the balance of energy per unit of time in the domain. The energy generated is the volumetric heat generation multiplied by the volume. In different domains, we can have different values of the volumetric generation. The inputs and outputs are those corresponding to the neighboring nodes. These can be nodes inside the solid, also boundary nodes. The question is, how do we calculate these inputs and outputs? It is convenient to formulate the energy balance by assuming that all the heat flow goes into the node. When solving the system of equations, we can identify which components are positive and which components are negative. To evaluate the conduction rate terms, we assume that conduction transfer occurs exclusively through lanes that are oriented in either the x, y, or z direction. We will use the concept of thermal resistance. Let's use a two-dimensions example. We mesh the solid with a square section so that there are 4 unknown nodes or internal nodes. At the bottom, the solid understudy is in contact with a solid base at a known temperature. We will identify it as node 5. On the sides and at the top, the solid is in contact with a fluid at a known temperature. We will identify it as node 6. In this 2D example, we obtain 3 components of the heat transfer rate between node 1 and its neighboring nodes. We can arrange the system of equations taking into account that the thermal resistance is the same whether going from 1 to 2 as from 2 to 1. Additionally, we are going to use conductances instead of resistances. Now, we can add all the inputs and outputs with the neighboring nodes. The result is a summation. The energy stored within the volume of domain 1, assuming there is no phase change, will be the heat capacity times the derivative of temperature with time. The heat capacity can be calculated, for each domain, as the product of the density times the volume, times the specific heat. Adding the different components of the energy balance per unit time in domain 1, the equation of energy conservation in node 1 is obtained. The result is a system of ordinary differential equations. As many as domains. The solution of the system of equation is the temperature distribution. In a steady state, it is a system of algebraic equations that can be solved easily. Heat transfer rate. We will see more in detail heat transfer rates calculations when studying the steady state and the transient regime. Summary. The energy balance method is based on dividing the medium into a sufficient number of volume elements. These elements are called domains. The node is the representative point of the domain. It is based in the assumption that in each domain the properties, the heat generation and the temperature are all uniform. For each domain, the energy conservation is applied. The result is a system of ordinary differential equations. As many as domains. The solution of the system of equations is the temperature distribution. Please watch the videos about how to solve a steady state and a transient regime.